Good afternoon. So how you doing? How's everybody? I really apologize for not marking your tests on time. I thought I'd sent them to the grader and well, he didn't get them. So I have to grade them because he started grading for another class of mine. And so I'm totally behind. But they look good, I have to say that. 3 weeks is really short for this course. You must be feeling it. I feel it too. I hope you're finding the time to get through all the videos. I just thought we'd meet today so you could ask me direct questions or I could solve problems for you directly. But essentially everything you need is in the video instructions, in the playlist for the live streams. And I've put up a mock exam that is an exam with the distribution of the test. Let's see if I can put that up for you. If I have it here. Here's a mock. Okay, I'll transfer it so you can see it. I'll just be posting it. Hold on. I use the same distribution every year. Okay, there you go. Alright, so this is the breakdown of the exam, and there's the mock exam that I put there, so it gives you an idea of what the exam will be like, and I have the solutions there. So the exam is predominantly on these units, but there are a few questions, 30% on the old stuff, the probability and the units 1 through 3. Okay, so it's 70% on the new stuff. I'm not sure what we can do. If you'd like me to look at the mock exam or answer specific questions, what do you think? What do you feel like me doing? So I've omitted the hypergeometric and Poisson problems, continuity correction factor. So there's going to be 16 multiple choice problems. Good afternoon, Yvonne. There's going to be 5 short answer problems and then 1 short answer that is a required. So you're going to have options here. You're going to choose 5 out of 7 problems to answer in the space provided. And then you're going to have a short answer problem here that everyone has to do, no choice. And that's going to be chosen from Unit 4, pages 42 to 48. That's the discussion of rules of means and variances. So how are you doing in your progress of reviewing the videos? So you're going to find the best videos for this in the playlist, right? Actually, I'll just write down, that's the tiny URL. .com. I can't even write it properly, but it's all one word, StatsLongobardiLive playlist. So I'm just wondering, oops. What you would like me to look at today. I can do the mock exam. Or do you have specific questions? The mock exam has the solutions. I provide you with the solutions. So this is what it looks like, right? So the mock is the same layout, same distribution of problems. Alright, so I'm looking at the mock exam because you haven't said anything. So you see there's 5, you solve 5 from the 7 options, and I have a regression problem and a problem on probabilities, and then binomial approximation, a problem with probabilities. Okay, so let's do that then. Let's solve from 5 and 6. So let's try these problems here, the longer ones. So I mean, I've made mostly videos of these, but these are, you just need to watch all the videos because it's all there. But let me see if I can do, let's look at this one. Again, these are in the playlist, right? So make sure you check out the playlist, all the videos there review a number of problems, so these will look familiar. So here, among Scottish people, the distribution of blood type is like this. In a sample of 12 people, what is the probability that exactly 6 of them will have type B or AB blood? All right. Use the binomial formula, so you get direction. Use the binomial formula to answer the above question. show all your work. This is question 2 of section 2 of the exam. So what you need to do, remember, for a binomial problem, you need to identify x and p and k every time. So if you can begin nicely by identifying what's a success. So what's a success with relation to this problem? What are we looking for, in other words? In a sample of 12 people, what is the probability that exactly 6 of them will have type B or AB blood? Okay, so this is what we're looking for. Type B or AB blood. And each time we look for type B or AB blood. The probability of type B or AB blood is this. 12 and 3 is 15%. 15% represents the probability of getting what I'm looking for, the success. So this is 15%. Then we're going to try looking for B and AB blood 12 times from 12 different people, right? And the possible answers are: no people have a B or AB blood, 1 person has it, 2 people have it, 3 people have it, 4 people have it, and so on. Okay, those are all the possibilities, 0 through 12. And we are asked to find what's the probability that exactly 6. So that's this one. So all I want to find is probability that x equals 6. Now for this part, for this final, you're going to get a formula sheet. I mean, you get to use all your notes, but if you use the formula sheet guides you. This problem applies formula number 1 on the formula sheet. The formula sheet that you have at the end of the exam is the same that's provided at the end of the notes for chapters 5 and units 5 and unit 6. This one here. Okay, so it tells you in this formula sheet that if x is a binomial with parameters n and p, so those are the parameters, because with those you will able to describe and estimate possible outcomes from the binomial distribution. So the mean and standard deviation, blah blah, this is what I'm interested here. The probability that x is a certain value is computed with this formula. I explain how I derive this formula in the videos. So what you do is you say the chance of getting, the chance of a person having type B or AB blood is 0.15. The chance of a person having B or AB blood is 0.5, so we want 6 of them to have that. If 6 of them have it, that means that out of 12, 6 of them don't have that, right? So the probability of not having it is 0.85. So then it's the number of ways of seeing 6 successes out of 12 possible successes, or 12 trials. Okay, so that is calculated thinking about how many ways, if you have 12 possibilities, is that 12? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if I was to lay out all the possible outcomes, the first one could have been success, the second is success, the third success, the fourth success, the fifth, and the sixth success, but all the rest failures. That's one way to see 6 successes out of 12. So I want to be able to rearrange all these ways, all the possible ways of seeing 6 S's sorted out of 12. So you could either list them or you can use your calculator to find them. So you punch in your calculator 12 NCR 2. Now 12 NCR 6. So depending on how your calculator computes that, you might have to hit the second function keys. So what do you get when you do that? Let's see if you guys know how to do that. I won't tell you the answer. So this is the number of ways of seeing 6 successes out of 12 trials. How do you punch this in? What do you get? Oh, sorry about that. Okay, so all I'm doing is multiplying this. So this is 924 times so 0.15 y to the x 6 times bracket 0.85 to the 6 close bracket times 924. Do you guys get the answer? Anyone? So when you solve these, solve them to 4 decimal places. What do you get? Do you get that answer? 0.0040. So it's a very small chance. Very good, Yvonne. So to 4 decimal places, that rounds up to 0.0040. Okay, so it's a very small chance. How about the next one? In a sample of 100 people, what is the probability that more than 20 of them will have type B or AB blood? So what I want you to do is now not a sample of 12, but a sample of 100. So you would have to do this for you would have to figure this out for 100, up to 100 people, and I want to know more than 20. So I want you to compute all the probabilities like we did above for all of these cases. So apply the formula that many times. So you'd have to set up something in Excel to do that. And there are tables, there were tables developed, books of tables before computers were created everywhere. So people used actual books of tables. You could actually find tables for the binomial distribution online if you search for it. But we don't have to do that. We have an alternative, and this alternative also was to replace needing tables or calculators to make these calculations. It turned out that we can use the normal approximation. Okay, so when we have to calculate using this formula many times, like more than 3 times, in this case we're going to have to do it like 79 or 80 times. 100 minus 21, yeah, 80 times. Okay, so rather than doing it 80 times, We are just going to use the normal approximation. How do we do that? Look at our formula sheet. The formula sheet tells us that x has a binomial distribution with parameters n and p when x has mean np and standard deviation square root of np times 1 minus p. It turns out that a binomial distribution will have a symmetric single-peaked bell-shaped curve like a normal distribution in a specific instance. It will be when n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. If those are both satisfied, then we say x is approximately, so I use the two tilde signs, then x is approximately binomial with parameters n and p. Sorry, what am I saying? Approximately normal with, I fell asleep, is approximately normal with parameters, the mean of which is np, and the standard deviation is the square root of np 1 minus p, and that is pretty much what this says up here. Okay, so n and p, x has a mean of np and a standard deviation of np 1 minus p. So this would be the mean and standard deviation even if these conditions weren't satisfied. So you should, if you don't know what I'm talking about, then you missed a bunch of videos about this because I did describe this. And it turns out that a binomial is approximately normal. So we're going to use that fact for the next exercise, okay? So I'm using still the first formula from the formula sheet. So what we're going to do is check first. Let's verify this is true. Let's verify that n times p, which is 100 times 0.15, is greater than 100. Greater than 10, and yes, it is. Right? Because it's 15. And let's see, n times 1 minus p is equal to 100 times 85, and that certainly is greater than 10. So these are both true. That means that we can approximate x as binomial, as normal, with a mean of 10 and a standard deviation. So this is n times p, and n times p 1 minus p square root would be the standard deviation. So we need to figure that out. So that's 100 times 0.15 times 0.85 and square root. I put that number up there. So 10 times 0.15 times 0.85 equals square root. So this is 1.292, if I did it right. Let me see. I do not have that answer here. Let me try that again. Is it 100 or 20? 100 people, 20 of them. No. 100 people, I have a weird answer. Okay, yeah, 15. Sorry, I put 10 here. This is not 10, this is 15. And then what did I do here? 100 times 15, let me try this again. 1 point, I don't know why I get those. Let's do that again. 100 times 100 times 0.15 times 0.85 equals square root. I have no idea where I'm getting my numbers from, so let me erase that. My repositioning. Okay, let me fix that. So this was 15, and then when you calculate this, you get 3.5707. Not sure why I made a mistake, but that's how I got that. Okay? So now we calculate the probability as though we're dealing with a normal distribution and answering the question, the probability that x is greater than 20 is what we want to answer. So it's an approximation. With an approximation, we standardize. This is z. And I take 20 minus 15 divided by 3.50707. So I standardize. So I'm going back to the normal distribution approach and solving the problem. And so I get that this is p z greater than 1.40. It's only 2 decimal places in the table, so I look that up. And when you look that up, thinking of the curve, you could look up negative 1.04 and find the answer. The answer is 0.0808. Right, so sorry for the mistakes, but let me know if you have any questions. Yeah, that's what this is. This is a 3.57 here. You're on. Any other comments? Should we do the next one? You can take a screenshot, and so I can continue. Okay, and this solution is in the solutions of the mock exam. The idea of the mock exam is you're supposed to sit on your own and attempt it without any aids other than the formula sheet, and then that will help identify where you need help, where you need to work more, study more, think more, where you need to put your efforts. Okay, let's see this one. Question number 3. A 6-sided die is loaded or weighted in such a way when it is rolled. The mock test is in the platform. You should be working through the platform. It's under modulo final exam, the last module. Where I have all the final exams to practice. So pull it out. We're on question 3 in the second part, section B. Okay, a 6-sided die is loaded or weighted in such a way that when it is rolled, it is much more likely to land with the side marked 1 facing down. Because 1 and 6 are not opposite sides of the die, this means that the die is much more likely to result in a 6 on the face that it is up. That is up. It has been established that probability of being up is 0.02 and the probability of 6 up, so 1 up is 2% and 6 up is 74%. All right, so we also know that the other 4 sides of the die are equally likely. So what is the common value for these? If these are for 2 sides and the total probability should be 100%, then 1 minus 0.02 minus 0.74 gives with me what? So this is 0.76. So that means, this is 0.76. So that leaves me 0.24. Okay, and so what's left is 24%, and I need to distribute that equally over 4 possible outcomes. So 24 divided by 4 is 0.06. So all of these other outcomes should have probability of 6%. All right? So now the next part. If you were to roll the die twice, what is the probability of getting a 1 on the first roll and a 6 on the second roll? So, point here is that each trial is independent. It means that the probabilities that we just sorted out here, where these are the probabilities for 1 and 6, and these are the probabilities for the others, figuring out the chance of an outcome on the first roll, you use these to figure it out, and on the second roll, you still use these to figure it out. It doesn't change. That's what independence means, okay? The probabilities, the distribution doesn't change from try to try. So it means the probability would be the probability of 1 and the probability of a 6. Now because it's sequential, on the first and the second roll, and the rolls are independent, this is how I figured it out. Because of independence, all I have to do is multiply. Okay, so the probability of a 1 coming out is multiplied by the probability of a 6. If they weren't independent, you couldn't do it that easily. So the 1's probability from the above the probability of a 1 is 2% and a 6 is 6%. So this is 2% times 6%. And so you get oh, sorry, 6. It's not two, it's 6 is 0.74 from the top. Right, from the information given. And when you multiply those, you get 0.0148. All right? Questions? If you don't have any questions, I'll continue. Okay, the probability, question 4. A simple random sample of 1,540 adults is selected from a population of 1,000,000 adults. The selected individuals were asked, do you happen to jog? Suppose that, in fact, 15% of adults in the population jog. So this is the probability of jogging. So jogging is the success that we're looking for. And this P, 15% is our P, the probability of success, jogging. So what do we do? So whereas in the other problem, what we talked about was the So in this problem, I use the binomial approximation on the number of people being more than 20. And I used from the formula sheet this result, which I derived in the videos, where this comes from. So what if you don't want the number of successes, so this is for number of successes, or what I call x. Let me say, this is for the count variable x. On the formula sheet, number 2 refers to p hat, the proportion or sample proportion variable. Okay, so that's for number 2. So the sample proportion, the theory on number 2 comes from number 1, because p hat is computed as a ratio of the number of successes in n trials divided by how many trials. So from the review of rules for means and variances in Unit 4 probability, you know that all you have to do is use the distribution of x, which is binomial, to determine the distribution of p hat. And it turns out that p hat has a mean of the true proportion and a standard deviation of this. So I can ask you questions about the count variable, the number of successes, or the proportion of successes. Okay? So that's what we're going to work with here. I'm going to use that to solve this problem. Find the mean and standard deviation of the proportion p hat. So the mean is from the theory, number 2 in the formula sheet, the mean of p hat. So I can write it like that, or I can just write it in words, is equal to p, which is from the above information you're told it's 15%. And the standard deviation of p hat from number 2 is p times 1 minus p over n square root, which we can solve for 0.15 times 0.85 divided by n, sample or 1540 square root. So you can figure that out. What do you get? And so what do you get for that? .0091. All right. Next problem. What sample size would be required to reduce the standard deviation to 1/2 of the value found in A? All right, this is the standard deviation with a sample size of 1540. And I mentioned in the notes in the SDS unit, this is all SDS material, I mentioned there that if you want to influence the standard deviation, you need to change the sample size, right? The larger the sample size, the lower the standard deviation of the sample proportion. Also, the sample, any results of the sample will be affected. The variance of the sample, the standard deviation of the sample results will be affected by the number of the number of observations. Okay, so if we wanted to reduce this to half, what should we do? Does anybody know? So how about this one? So if I wanted half of this amount, that would be the same as Does everybody agree? So if I wanted half of whatever this was here as a standard deviation, then I would have to put this inside the square root. In other words, another way to look at that is that would be 4 times the sample size. So you would have to multiply the sample size by 4 to get half as a standard deviation. Do you follow that? So if I wanted to get 1/10 of the standard deviation, then I would have to multiply n by 100. I have an expression explaining if you want 1/k, then you have to multiply it by k. Sorry. Yeah, k squared. Because of this square root sign, if you want 1/2, you have to have 2 squared, or 4 times n. Okay? So if you want 1/10, so 1/10, then it's 100 times n. Get it? So what's the answer then? 4 times n is 4 times 1540. Is equal to 6160. All right? So the first part of the problem was using formula 2 of the formula sheet. This result you should add to the formula sheet if you understand it. So you should have the formula sheet at your side, and you should add formulas onto it or build up the ones that are there. I actually added more comments to the formula sheet on your in your notes, so I would recommend using that one. Okay. The final exercise is, so this is from Formula 2. This is a result of Formula 2, I guess. And then use the normal approximation to find the probability that between 13% and 17% of the sample jog. So all these results they arise from the normal approximation. I didn't check it officially, but I should have, I guess. You should always check that that's true. And it is going to be true. N times P is greater than or equal to 10, and N times 1 minus P because N was 1,540 times 15% is bigger than 10, for sure it is, and even bigger is N times 1 minus P. Okay, so this is true. So I'm going to use a normal approximation. I've used it here. That's the result from 2, because 2 derives from 1, which is an approximation, the result. And then to figure out the probability that P hat is in between 13% and 17%, you use the results in part A to standardize your results. So the probability would change to 0.13 minus 15% divided by 0.0091. That turns P hat into a Z, and then 0.17 minus 0.15 divided by 0.0091. That's it. Simplify and then use your tables. Let me make this clearer. Okay. Then you standardize it now. Solve it. So 2.2 and negative 2.2 is this area here. What do you get? So the area here is 0.01939, and then over here is, to the left, is 0.9861. So this is the 1.39 percentile, and this is the 98.61 percentile. So I use the approach of big minus small to get the inside part. And the answer is .9722. Okay, questions? See the next one. So the problems end up resulting in the normal distribution. If you watch my videos, I encourage you to do and to understand the normal distribution well, because you use it to the very end of the course. It's the backbone to a lot of what we do. Alright, so now we are in inference. Let's see. This is question number 5. Do I have only 2 problems here? 3, 5, 6, 7. Okay. A process that produces bottles of shampoo, when operating correctly, produces bottles whose contents weigh on average 20 ounces. A random sample of 9 bottles from a single production run yielded the following content weights in ounces. Assuming that the population distribution is normal, test at the 5% level against a two-sided alternative that the null hypothesis that the process that's a weird sentence, isn't it? Assuming that the population distribution is normal, test at the 5% level against a two-sided alternative that the null hypothesis is processing correctly. Okay, the two-sided, the alternative is that the process is operating correctly. I see, okay. State the null and alternative hypothesis. Compute and, okay, so I explained that when I ask you to do this the long way, if you have an alternative that is two-sided, you don't have to do this the long way. However, here I'm very specific. I asked you for the test statistic and the p-value, so I asked you for all these parts. So in that case, what I want you to do are the 5 steps, what I call HAPC. So H stands for hypothesis. So for all these problems on inference, the hypothesis is always set up like this. You put a parameter here, in this case, and you should read every problem to identify what parameter is of interest. Now, we focused in this course on means and proportions, so the parameter of interest for this problem is the mean, right? Because we have weights. So we're going to use the mean. So whatever I put up here, I put up here. So that's the population mean. And whatever number I put here, I also put here. So to operate correctly, they should be on average 20 ounces. So that's the number I'm going to put here. And whatever I put up there, I have to put here, okay? And I'm going to test it against the alternative. It tells me the alternative is two-sided. Two-sided looks like that. So the null hypothesis is the status quo. It's what we want to test. Does the status quo still hold? Is it true that it's 20 ounces on average? Or is there evidence to refute that? The alternative is that it's not. This just means not that. All right? So whereas the null hypothesis means no difference or nothing new, the alternative is that it's not correct and there is something new. So we want to test to see if we have evidence against 20 as the average, 20 ounces as the average. So that's the H step. Then we assume. What do we assume? Well, we can't do anything here unless we put, unless we how do I say? We have to stick our neck out. We have to make a statement and then test the statement. That is the nature of the scientific method. We make a hypothesis, we believe it's true, or we assume it's true. In this case, we're going to assume H not true, and then we are going to proceed to check in a sample if the sample accords or supports our result. So H not true means mu equals mu naught. These are mu naught. These are mu 0, okay? Is equal to 20. But I have no other information. I just have the information here. When you have no other information, meaning you don't know the distribution from where these measures came, you don't know you have no information about the distribution, you don't know we're testing their mean, and here you don't know their standard deviation. When you have nothing, you have to use formula number 6. So I explain all of these in the videos in the playlist. I really hope you get through them. We're here. Because you notice if I use these formulas here, I need sigma. I don't have sigma. I don't have the true population standard deviation given to me. Okay? So all of these formula here are for inference on the mean, where mu and sigma are unknown, of course. I mean, mu is not known to be able to do this. No, sorry, I wrote that wrong. That's below. This is inference on the mean, mu. I'll just write sigma known. So you don't know mu, but you do know sigma here for these formula. You see, because you use it in the formulas. If you don't know what these formulas are, go back through the videos to learn. 6, inference on the mean. Sigma here, though, is unknown. If I don't know sigma, I have to use the best guess, the best substitute for sigma. The best guess, best substitute for sigma is S, the sample standard deviation. So I'll use that instead, all right? But when I use that, I no longer get to use the normal distribution. I have to use this special distribution T, and I described how to use that in the videos as well. So I refer you to those videos, but I will solve the problem anyways. So we're going to do the next step. We're going to assess the evidence. A for assess the evidence. Assessing the evidence is assessing the sample. The sample is where we get the standard deviation from, the mean and standard deviation. So X bar and S from the sample must be calculated. So use your calculators the way you learned in stat mode to calculate the mean and standard deviation. What do you get? So you should be using your stat mode of your calculator to enter those values and find X bar and S. Okay, so there are 1 decimal place in the values I give you, so I'll keep up to 3 decimal places, right? That's what I explain in the notes. So I'm going to use 20.356 as the mean, and the standard deviation is 0.613. The other thing that you need to evaluate is the degrees of freedom. Degrees of freedom is the sample size minus 1. In this case, the sample size is 9, so degrees of freedom is 8. And what we have to do is take this 20 and ask ourselves, well, is 20 close? This is the average, the sample mean. Is this good enough? Is this just the same as 20? Like, is this, how do we determine if 20.356 is just 20? So we haven't found any evidence, any evidence against the hypothesis. Well, it depends. It depends how much variation is in the numbers and whether 20.356 is just as good as 20 or if it's significantly different, if it's far enough away. And the only way we're going to determine that is to look at how spread out the distribution is and adjust for how spread out it is and speak about if this 20.356 is in normal keeping with the variation of the variable as presented in the sample. That's all we have, right? So what we're going to do is standardize this value. We're going to standardize this value using S, and that'll give us the number of standard deviations away from the mean, the hypothesized mean. And okay, so that's what we're going to do next. So this gives us the test statistic, and the test statistic is a t statistic, okay, because we're using S. We're going to take the x bar minus, let me make that clearer, minus the hypothesized mean and standardize it with its standard deviation. Now this S is the standard deviation of the sample results, or it's the standard deviation of the weights, right? But I want to know what's the standard deviation of the mean weight. This result is actually formula number 3 from the formula sheet, where I take the standard deviation and divide by n. So anyway, again, review my videos. So this is the standardized value. So it's going to be putting in the numbers 20.356 minus 20 divided by 0.613 divided by n is 9. Okay, degrees of freedom is something different, it's not n. So when you compute that, that tells you how many standard deviations you are away from the hypothesized mean that you're treating as the true mean. And what do you get? What'd you get? Excellent. 1.743. So 1.743. And now what do we do? This is on the t distribution, so we need to take that number to the t distribution, which is here. Now what does this do? So I do review this distribution. These values here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are 12 values that are laid out in the upper tail, the upper right side of this distribution. Now it looks pretty normal, right? So it is symmetric and single peaked and bell shaped. However, it's much more flat than the normal distribution to begin with. So it's more like that. Now as you have a larger and larger sample size, this ends up becoming more normal-like. Going more like that. Okay? So it becomes more normal. And you see that as the sample size goes up, where degrees of freedom are n minus 1. So you could look at this column as calculating or characterizing the sample size increasing. And at the very bottom, what you see is z. You see? So as the sample size increases, the t distribution just becomes the normal distribution. So I pull these out of the normal table, the standard normal results, for high sample sizes. So sample sizes more than 1,000, you just assume it might as well just be normal. And so what does this give you? So these give you, notice, if I was to draw these out, these are for upper tail beginning at 25%. So 25% upper tail. So this is the top percentile, right? 25%, 20, 15, 10, 5, and then it goes in half, and then it goes a little bit slower. Okay, to here. So what you're doing is you're moving over the numbers in the chart, move you closer, like more away, you know, more in the extremes as you go this direction. As you go in that direction, the numbers go in this direction. Okay, so it leaves a less and less upper tail. So you just got 12 values here, and then because the the distribution is symmetric, you also have the negative values and their probabilities. All right, in the table you can infer from that. So where are we? We are degrees of freedom 8. So we are going to focus on this row 8, and we're going to look for 1.7. So it's not here, right? 1.74 is not here, but it's in between these two. So, you know, you could find this on Excel. I put the code on the Moodle page of how you can type this in and get this out of Excel, or you can figure it out yourself. In a cell, you can just press in Excel, in just one cell, press the equal sign and ask for the t distribution. It will ask you for the degrees of freedom, and it will ask you for the critical value. These are the values that are on the line, and it'll give you back a probability. Or you can do it in the reverse, where you give it the probability and it gives you the t critical value, or the t-score. So it's between these two, and that's the best we can get from this table. If you use Excel, you can get a precise value, but this is fine for me. You would say between 5 and 10% would be the area. That's the best you can do with the table. So you say the answer is 2. So that's okay. So what we've done is assessed. We've assessed by calculating the t-stat, or the test statistic. And what we need to do next is get the P, right? So going back to my acronym, my mnemonic device, HAPC. So we've done hypothesis, assume, assess, and now we're going to do P. The P is the p-value. So p-value is the probability of seeing a test statistic as extreme or more extreme given H not true. So what we're doing, I write that out, you don't ever have to write that out, or maybe it might appear in a multiple choice problem, but what you want to do is you want to figure out the chance on the T, in this case T8, on the T8 distribution, you want to figure out the chance, probability of seeing a test statistic as extreme or more extreme. So what it's saying is go into the tails in the direction of the alternative hypothesis. So from here with a p-value, you always use p-value together with the alternative hypothesis. So, because we didn't use it until now, did we? We're going to use it here. So going back to the alternative, remembering we were told to check the alternative of two-sided. So what we do is we test to see if it's extreme. We plot the test statistic here, and it was 1.743. Make a mess of these numbers. That's 1.743. And I'm also going to put it here. So what I'm saying is 1.74 above and below standard deviation. So standard deviations away from the mean, where the mean is in the center. There's a 0 here, even in the t distribution, and I'm trying to see what's the chance that of being out here. The chance of being out here, well, we figured out the chance of being here, and it was between 5% and 10%. And the chance of being here was between 5% and 10%. So the chance of being as extreme or more extreme, higher or lower, is the double of those. So my suggestion for doing this is that you draw it. Okay, so every time you draw it, so you remember how to do this. So that concluding, the p-value is 2 times 5% to 10%. Somewhere in between there. I'm not going to be precise for the test, you just use the table, but you can in life use Excel if you want, of course. So the probability is between 10% and 20%. All right? So between those, so now how do we conclude? So it's saying that the chance, given, assuming H naught is true and using it as the hypothesized mean, as our mean, we figured out that we are 1.743 standard deviations above the mean. The chance of being there or away from the mean in the other direction, the chance of that happening is 10 to 20%. So now we have to say, is that strange Is that bizarre, unusual? Or is that in keeping with the null hypothesis? So what is considered unusual? The last step is C. C is the concluding step. The conclusion is always that this is always the conclusion. This is the way you make your conclusion. Well, I mean, you have to write it out in words, but you use this to test. If the p-value is smaller than a preset level, so if it's very unlikely that you would have seen the test statistic that you saw, then if it's very unlikely, but then we did see it, we have a problem with something. Either we have a problem with our sample, or we have a problem with our assumption. Since we have taken precautions, or you're going to assume that there's no problems with the sample, the problem must be with the hypothesis, okay? So we reject the hypothesis, the null hypothesis. Now, the only question remains, what is this preset level that we're going to compare to? What's going to be considered unusual? Well, if its chance of appearing was only 5%, and it appeared, then we're going to say that's unusual. So use alpha, which is known as the level of significance, of 5%, unless I tell you otherwise. This is the level of significance. Okay? So let's test. We got our answer was between 10% and 20%. Is that smaller than 5%? No, it's not. So we're not going to reject the null. We haven't found evidence against the null. Our result wasn't unusual. It wasn't an unlikely chance. It was, it was a common occurrence according to our preset notion of unusual, a 5% chance of showing in the end. But in this case, it's not unusual. What we do is we say fail to reject. So now we have to conclude that the test is not significant. We didn't find anything significant, anything new, anything to report. And in the language of the problem, we have to go back to the problem to answer it, directed in the terminology of the problem. What did we find? Can you guys give me a statement of what we found? Where is the statement? The original statement was about shampoo bottles. So these were the weights of shampoo. So there's really insufficient evidence to say that the weight of the bottles is different from 20 ounces. Okay, so there's no evidence that that's true. That's what you would say in your final statement. I say an average. Okay, so there is insufficient evidence that the shampoo bottle weight is different from an average of 20 ounces. Okay, hope you can read my writing. It's easier for me to write with this stylus. Hopefully I can get a better iPad in the future. All right. Questions? Can I go on to the next one? You can take a screenshot so I can go on to the next one. All right. How about this one? So 2 more. A brochure advertising for a new diet program states that the participants are expected to lose over 20 pounds in 5 weeks. A random sample of 25 participants is selected, and the number of pounds lost in a 5-week period is determined for each. These weight losses have a sample mean and sample standard deviation of these pounds. It is of interest to test if the population mean weight loss from 5 weeks of participation in the program is greater than 22 pounds. Alright, so this is a problem of inference. This is a hypothesis test, which I always express and it's for means. So I didn't do any proportions here. This is for mean, and I'm going to test. It's always an equal sign, I told you, right? So that in the null hypothesis it's always equals, and then whatever number I put here I also carry on here. The number that the status quo, what we believe to be true, we want to test if over 22 pounds are lost. So we're going to use the number 22 here and 22 here, and we're going to test to see if participants lose more than 20, because that's what it says here. So because I'm restricted to putting an equal sign here, that's going to be 22, that's going to be 22, and the greater sign goes here. All right, so I have been given information. So this is H. This is the HAP-C steps. This is my H step. Now I can assume H naught is true. If H naught is true, then notice, because I've been given sigma, I don't need to use this S here, okay? Sigma is preferred to S because it's the true one. So now the formula I'm going to use to evaluate is this one, number 5. this row here, or this one over here, because this is for sigma known. I'm going to do the same process, but I'm going to use the standard normal table instead of the t-table, and I'm going to use sigma instead of s. So since h0 is true, then x, where x is normally distributed with a mean of, now we assume the null hypothesis to be true, right? So the mean is 22 and the standard deviation is 0.5. This was given to me. So that means in a sample of size 25, the sample mean is distributed. Does it say anything about normality here? Yes. It tells you approximately normal. So the sample, so this is saying that this is approximately normal. So that means the sample mean is approximately normal with a mean of 22 and a standard deviation. Now to get the standard deviation for the sample, this result comes from formula number 3 on the formula sheet. So like we just use everything on the formula sheet. This result comes from here, where I explain if x has a mean of mu and a standard deviation sigma, the sampling distribution of x bar, so x bar's distribution, it has a mean, the same mean, and a standard deviation that's smaller by a factor of root n. Okay, and these will be normal if x was normal, and even if x was not normal, x bar's distribution would be approximately normal as long as n was large enough. So, you know, review those videos, review those concepts, but that's in there and in the notes. So that means that the new standard deviation would be sigma over root of n, which is 10.5 divided by square root of 25, or square root of 5. So 10.5 divided by 5 is 2.1. Okay. Two point one. So that's from assuming. Now we want to assess. Assess the evidence assess the evidence means standardize your result. Our result is the sample mean that they give you here, see? You have to distinguish between the sample results and the population results. These are population results in the blue. Well, I have this one in red. Let me see if I can erase it. Won't let me just erase it. Oh, anyway. I'll put this one in red. So those are the population results. In the blue, that's the sample result, okay? So you have to distinguish between the sample and the population to do this correctly. So the sample result, in the sample you got 26.4 as the average weight loss. So that's quite high, right? If we are just testing to see if it's higher than 22, it looks like 26.4 is high enough, but in statistical terms, we need to know if that's sufficient. Look how large the standard deviation is. Okay, so in numbers of standard deviations, that's not significantly different, it looks like, from this, right? Because one standard deviation is like 10 away from 22. So let's see, let's verify what it means. So let's assess. We assess to calculate a z-stat, test statistic. And remember, statistic is computed from the data in a sample. So the z-stat, you take your sample result and you standardize it. You divide by the hypothesized mean and divide by the new standard deviation, which in this case is sigma over root n. Remember, it's not just sigma, okay? It's for this, the point is it's for the sample mean. All right, so we standardize that as 26.4 minus 22 divided by 2.1. What do you get? It's 2.09 or 2.1. All right? All right. Now what? The p-value. Draw a picture. The p-value is the probability of seeing a test statistic as extreme or more extreme given H naught is true. So what am I talking about? I'm talking about this. Now I take my Z, now we're on Z, okay? And I mark 2.1. Now I'm only going this way. I'm not actually, let me erase that. It's going to confuse you. So I'm only going on this side. Why am I only going on this side? Because I use HA. HA had a greater than sign, so I'm going to test the extremity of the right hand tail. So basically I'm checking it to see if it's higher. What's the chance of being higher than 2.1 standard deviations away? That's really far away. What's the chance of being that high? So you can test the probability that Z is greater than 2.1. Look on your Z table, and what do you get? Anyone? No one? It's very small. It's 1.79 or 0.0179. So it's very small. This is known as the p-value, right? So that's the chance of seeing a t statistic, a z statistic or test statistic. So the chance of being 2.1 standard deviations above the mean in a sample that was supposed to have a mean of 22 is very unusual. Okay, so this actually is saying 26.4 is different according to this. So how do we conclude? Concluding step. A concluding step using the statement I gave you. The p-value is 1.79%, and it's less than the preset 5%. So we do reject H0 in this case. So what have we concluded? So there is sufficient evidence to suggest that weight loss is greater than 22 pounds. In this case, we say test is significant. We can write the there is sufficient evidence to suggest that weight loss is greater than 22 pounds on average. Or that the average weight loss is 22 pounds, or greater than 22 pounds. Keyword. Okay? All right. How's that? Questions? Okay, no questions? Should I continue? All right. 3 students in a large school division are giving a spelling test at the beginning of the year. They're giving another spelling test at the end of the year. A sample of 30 students is selected, and a hypothesis test is to be conducted to determine whether there is significant evidence at alpha equals 0.05 that the spelling ability has improved. The mean difference in scores is in the sample was 2.4, and the sample standard deviation was 8. So these are sample results. Okay, those are not population results. So what we've done here, what we've got are mean differences. So in setting up this test, it's slightly different because you notice I don't have a hypothesized value. There's no numbers here. But whenever we do a mean difference test, what we're saying is a test for mean equals 0. So the difference, so for no difference, the status quo would be a mean of 0. Okay? And then because I put 0 here, I have to put 0 here. And what I'm looking for is an improvement. Now, how did we subtract these? Okay, we'll assume that they subtracted the new one from the old one, okay? And so we're checking to see if the new one, the new score minus the old score, is greater than 0 for an improvement. Alright, so then, what do we do? We assume and assess. Assume H naught is true. So what you're going to do is assume that the difference, the mean difference, is 0. Since you don't have any other information about the population, again, this forces you to use the formula in row 6, this one here. Okay, so for the t distribution. So we don't have any other information. So we're going to, whenever I use the t, I just put these together. Assess the evidence. What's the evidence? We're going to assess if 2.4 is significantly different from 0. And we're going to standardize 2.4. So we're going to calculate a test statistic as a t statistic. And it is equal to x bar minus the mean, hypothesized mean. So it's the one over here. That's what these are. And you standardize it using the standard deviation of x bar. Because we don't have sigma, we use s instead. So putting it all together, x bar is 2.4 minus 0 divided by s, which turned out to be, let me go get it, 8, divided by square root of how many pairs? How many were calculated? 30, okay. 30. And we have to just assume there's no other information, so we just assume that this comes from a normal distribution, or that it's not highly skewed in test scores to be able to do this. So we calculate that. Which turns out to be 1.64. The next step is the p-value. So is that significantly different? Is that far enough away from 0? Is 2.4 strange enough or high enough? I don't think so, but let's see. The p-value would be calculated, again, as the probability of seeing a test statistic as extreme or more extreme given H not true. So we draw a picture. We put our test stack on the picture and we go in the direction according to the alternative hypothesis is greater than, and you find the probability here. So what's the probability of being 1.64 or higher in the T29 row of the t-table? So you tell me that. Someone tell me what that is. What is it? What do you get? So you go to the T29 and you look for .64. It looks like it's between these two. And what are those two? That's between 10 and 15%. Okay, if you look at the top, it's between 10 and 15%. No, that's wrong. Between 5 and 10%, sorry. Okay, you go all the way down. So that's between, those areas between 5% and 10%. So the p-value turns out to be the probability that the T29 table is greater than 1.64, and that is between, so I don't expect you to write it like this, but I do expect you to give me the value. I would like to see the graph as well. So that's the answer, between 5 and 10%. No, was it 5 and 10? Yeah. It's so funny. Yeah, that's right, 5 and 10%. All right, so finally conclude. In the concluding step, notice, in the concluding step, no matter if I'm going greater or less or not equals, I always evaluate using p-value less than or equal to alpha means reject H naught. Okay? And if you don't, if that's not true, you fail to reject H naught. So our case is 5 to 10% is not smaller than 5%. So you fail to reject. So what does it mean in the context of the problem? The test is not significant. The test is not significant, or the test score did not improve. Okay, so there is sufficient evidence to, no, there is insufficient evidence to suggest the test scores improved. Or the average test score. Improved. All right. How's that? So we've done all the long answer problems. You do need to go through and review all my videos. I've covered in greater detail the origin of all these formulas. Do I have to do the last one? I think I do the last one. I give you the solutions to the last one. Are there any other problems on the mock test that you would like me to do? So this is pretty much what it's going to look like. On the final, it's going to be like this. Yeah, the mnemonic I've been using is HAP C. HAP C. So hypothesis, assume, assess, p-value, and conclusion. And I want to show you, if we go back to the exercise, the first one that we did, so this problem was a two-sided test. Okay, so for the two-sided test, we had to test both sides. Now there's a faster way to do this, unless I ask you explicitly for the 5 steps, and I'll ask that like in here in this problem number 5. I ask you to show, compute the appropriate test statistic, compute the p-value, and then a carefully worded conclusion. All of that, HAPC will help you get it. But if I don't specify all that information, you can do this a lot quicker. Do you know how? If you have a two-sided test? So you should be, reviewing my videos in the playlist, not just the ones in the Moodle. Okay, I made playlist videos. I don't know what else to show you guys. It's all there. Everything is on YouTube. This whole course. Just gonna write it again. So I don't know what else to do. tinyurl.com/stats Longobardi live playlist. So these videos that I'm making, I told you to start back at an earlier date. Go as far back as you can, and I have timestamps. So everything after the midterm, April 9th, or April, let me see. So all the videos in this playlist, you can start at okay, so April 1st gives you still the review of for the test, and I think they did the test on the weekend. So April 1st is a review of the test. I have all the timestamps in there. April 6th. April 7. So April 7, right? So if you start on April 7 and watch all those videos, there's an hour a day. I get through all the material. So start on April 7th. So I asked you a question. What's a faster way of solving this problem? The faster way of solving this problem is to make a confidence interval, build a confidence interval around these values. So let's do that. The formula for confidence interval is in the first column of the formula sheet. So here are the formula for confidence intervals. So we're going to build a confidence interval using either this or this, depending on whether we have the mean, the standard deviation of the population. Okay, so what do we have again? We calculate t-stat. Okay, so we're using the t. So compute the confidence interval for these numbers. What we need is, we already have the mean and standard deviation that we computed here. So we don't have to do all this other stuff. All we have to do is create a confidence interval for those values. Confidence interval looks like so this means create this is the standard deviation, or we call it the standard error. This is the standard error for x bar. And this is x bar. So this is, standard error is just an alternative term when you are using a parameter inside of a parameter. An estimate inside of a parameter. This is supposed to be sigma. Look, I put a z. I gotta fix that. That's not a z, right? Let's do this properly. It's x bar plus or minus t star s over root n. If I'm going to use s, I have to use t. So this represents the standard error, which is just the standard deviation with an estimate inside of it. And this is the sample mean. So this is the standard error of the sample mean. And what we're doing is making an interval of so many standard deviations from the mean. That's what we're doing. So this is the so many. 1 or 2 or 3 or 1.4 or 1.5. So what determines this depends on the confidence level you want. I get that number from the critical values in the t table. The t table is here. So if you go to the bottom, you see all these different levels of confidence. I explain confidence intervals in the videos. So in this problem, we did a test with 5%. If alpha is 5%, that means that you're testing against 5% total in the tail, so 5% error, in other words. You're allowing for 5% in the tails. So that's 2.5 on each side. Or in other words, 95% confidence in the middle. So what we're doing with a 5% hypothesis test, if it's two-sided, we can calculate a 95% confidence interval and use it to assess our evidence. So a 95% confidence interval, depending on the degrees of freedom, will determine which one we pick. So if we go back, which one do we want? How many observations were there in this problem? Degrees of freedom was 8. So we need the T star for 8. What's the T for 8? And 95 degrees of freedom. The T critical value. So let's see. It's here. Oops, 2.306. 2.306 would be for 95%. All right, so that's what we're going to use. So basically, to have 95% confidence, you have to be 2.3% away from the mean. So we have all the numbers. We have this one is 2.306. Is that what I said? And this one we have already calculated over here. And then S we've already calculated, and N is 9. So create the confidence interval for me, and then we'll interpret it. Okay, I'll give you 5 minutes. What? You guys didn't get it yet? You can't calculate the confidence interval? Come on, one more minute. All right, here we go. You guys are not doing it. So the X bar all right, so it's going to be 220.356 plus or minus 2.306 times S over root n. S is 0.613 and the root of n is 9. It's like that. So simplifying this, all of this is called the margin of error. Let's calculate the margin of error together. .613 divided by 3 equals times 2.306 is 0.4711. I'll just leave it. And then plus or minus 20.356. So this is the 95% confidence interval. So what I'm going to do now, so this is saying that give or take 0.471 will give you an interval of values that are close to 20.356. So they are within 2.3 standard deviations from the mean. And I figured out that I got to go 2.3 to get 95% in the middle. So 20.356 minus 0.471 is 19.885, comma 20.356 plus 0.471 is 20.827. So that's the interval. Anybody get that? Now with that interval, now use check. Check if the mean hypothesized, the 20, is in there. Well, let's say we look for it to be outside. Only if it's outside of the interval is the test significant. So because 20 is inside, So you say since 20 is inside, it means that 20 is not different from the values in the interval. So it gets captured in the confidence interval around the sample result. So since it's inside, the test is not significant. We didn't find anything unusual. All right, got that? So this is how you test. You do this test only when use the confidence interval for two-sided hypothesis. All right, how's that? So you got the same result if you do it this way with the interval, or if you do it the long hap-C way. The only way I was able to do it easier in the corner of a page here was because it was a two-sided test. Okay, it's 7:45. You have an idea of what the test is about. Watch all my videos. I don't know how many hours left, but really everything is there. Ask me if you have any questions. I'll make additional videos if you need anything, but find the time to watch those videos, okay? You can watch them in fast motion. Maybe I'll have the time to put the timestamps on so you don't have to waste time looking for things. If you don't have time to watch it straight through, maybe I can do that for you. So then you just click on the timestamp in the description and it'll put you into a video about probabilities or binomial or whatever it is. Okay, so on April 7, I start all the videos relevant to this for the test. Okay. Any questions? Okay, no comments, no questions. Yeah, I'm going to go. And please keep in touch. Email me if you need anything. I can do, well, I said I would post the test on Sunday and you can give it to me. What did I say? So Sunday I will post it. Or I think I said Saturday I would post it. What did I say? I'm going to post it Saturday and then you can get it to me by Monday. Remind me what I said. So that you could have the weekend to work on it. Yes, the grades. I know you need the grades. Okay, Saturday. All right, very good. So I'll post it Saturday at noon, and then I can have it. I said Tuesday to Tuesday morning. Is that what I said? Wow. Yeah, because I need time to mark it. You see, there's really no time to mark stuff. And I have another class I'm giving too. This is my big problem. All right, so Tuesday morning, have to get it. Okay, so Saturday at noon. Is that what I said? Till Tuesday. Saturday at noon to Tuesday at noon. Is that what I said? Saturday, Sunday, Sunday to Monday, Monday to Tuesday. We have 4 days. All right. Okay, so have a good night and watch those videos. I'll work to put the timestamps on them. Okay? Good night.
A whole day now, that's my life.
Well, I mean, like with kids. But yeah, you've been on
6
here all
hours.
day. Okay, call Mom. Talk to her. Tell her to relax.
But the problem is I close it from
I don't know. Bye, have fun. Mom, why are you mad? Why are you mad? Why are you so mad? No, I said, why are you mad? Why did you write that text about the Americans?